Here's our cheat sheet for exam number 2. And there are a few new things on here. Okay, and pretty much this stuff. Okay. Okay. So we have a particle in the box. And we have a wave function for it. Right? If you're going to draw the box, you pretty much draw something like this, right? And they're trying to say that the potential energy is infinite outside of the box, and we've kind of had this kind of thing before. The equation that we're going to use is the math equation. The wave function is this. Does it look normalized, Kevin?
Which one?
This wave function in one dimension.
Yeah.
Yeah, because there's a little something out here, right? It's not just the sinusoidal part or the exponential part. You have something out front. So, yep, it's normalized. And you could prove it by just saying integral from, right, 0 to L, psi star psi dx. You get 1. Okay, it'll work. And if you apply some operator, Mel, we can get this as an eigenvalue. What's the operator?
Oh, Hamilton.
The Hamiltonian, the little h hat. And you're going to have, do you have this in your notes? Oh, wow. I'll have to, I can print it out for you. You don't have handout A.
Sure. Is that the end of this chapter?
Maybe it's at the end. You don't have handout A?
No.
Okay, I'll have to print it out. But in handout A, this is going to be the homework for Monday. See, handout A, you're going to derive that. You're going to start with the wave function for a particle in a box. You remember the one that Kevin said is normalized, and you're going to, derive and get the energy, right? So what would be the starting point for something like that? Jeff, what would be the starting point to get this?
To get the
Yeah, to answer this. Yeah, the very first thing that Smith is trying to get you to write. The general expression, the starting point. What would be the general expression?
Would it be like omega hat F equals?
Okay, now this. Eigenvalue. I think that works if, yeah, this would definitely work if we pick 1F. But see how this has a little counter on it, right? A little n, right? So there's a whole bunch of wave functions. So if there's a whole bunch, you're going to calculate the A word, average. So that's really what you're doing. So you're right, man. That would have worked if we could erase that little n there. But then we'd have to erase the little n in here, too. But no, this isn't it. If you want to get an average, it's going to be what starting expression. We never said average. We called it, started with an E. We said expectation value. Kevin, what was the expression that you're supposed to write for expectation value? And that's the same as average. This is a fancy way. This is job security here.
Omega hat equals the integral.
Yeah, but something was surrounding omega hat. Yeah, the bra and the ket there.
Integral psi star omega hat psi beta.
There it is. That's your starting point. Yep. And then you'll get the energies from it. Okay. So that's what you'll be spending your weekend on, is deriving that, one of those problems. Okay. And then, so for this particle in a box, can it take any energy, Gloriana? And energy is supposed to be in what units? If we did all this, what units would you end up with here?
Joules.
Joules. Can it get any energy you want there, Mel?
Can I get one?
Can I have any energy I want for that particle in a box? Yeah, there's the problem. N can only be 1, 2, 3 on up. So that's your problem. So the energy's quantized. So you're going to have an E1, an E2, an E3, and each one's going to have a different energy, which is good, right? So that means wavelength number 1 is going to have its E1. And this is, if you wanted to actually get it, this is where you could apply what Jeff said. Well, I can't draw omega. That would follow that format, right? So that you could, each wave function will have its own individual energy. Okay. And then, I don't know why that even mess with this, because for N1, I'll just pick N1 and N2. They just differ by 1. N1 and N2, N2 and N3, N4 and N5, whatever. You just subtract the 2, and you get this expression. Well, we could have just substituted it in here and subtracted the 2, right? Same thing. But that's okay. Let's take a look at that animation here. So we've kind of played around with this once before. Here's our particle in a box, and the plot down on the bottom is our wave function or probability density. What is it set up to look at? Probability density. Yeah, because you see it says it right over here. You want to see the wave function, you click on that one. We're looking at probability density. So psi star psi. Okay. What happens if I make that box really, really big? I really spread it out. What happens to the energy? Make that box huge. The bigger you make the box, the energy starts approaching what number?
0.
0, right? Because L gets bigger and bigger and bigger and bigger, the energy gets 0. Visualize it, right? So if I make the box bigger, what happens to these? What are these green lines? Energy levels. And I can, I only have a few here, I can see what each one looks like, right? I get up here, right? The yellow's the probability density, right? So what does this mean again? For this state, what is it? 1, 2, 3, 4, 5, 6, 7. For n equals 7, what does the probability density mean again?
Probability where the particle might be.
Yeah, what the probability might be. So if you do something a little that's easier mathematically, I want some more integers here. So there's 1, 2, 3, 4 sections. So there's 25% probability that it'll be here, 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 or there, on average, where you'd find it, right? And then there's the spots where there's a node you're never going to find. It's supposed to observe. You're never going to observe it there, right? That sort of thing. So as the box gets bigger and bigger and bigger, the energy levels the difference between the energy levels becomes smaller, much smaller. I mean, if you get it to be a macroscopic size, can you tell the difference? Is there any quantization of energy?
No.
Yeah, you can't tell. They just run into one another. Okay, so that's the mathematical games that they play with to try to make things make sense in our macroscopic world. Another oddball thing, I think, is you have this particle in a box. And here's what n can be. Mel, can the energy ever be 0?
No.
No.
There's always a number.
Yeah, so the lowest energy you can get is h squared over 8ml squared. Does that make sense? What's 0 Kelvin? What's so special about 0 Kelvin? You hear that? You have the absolute temperature scale. Can you get any lower than 0 Kelvin?
No.
Well, if you make things colder, how do you make things colder? What's actually going on?
The molecules are not moving.
Yeah, they're moving around less and less and less. That's how you make things colder. They're just moving around less and less and less. So at 0 Kelvin, does that mean things have stopped moving? According to this, the answer is no. There's always a 0 point energy. And you can't get any lower than it. Okay. So if one way in our macroscopic world, L would be huge. Right? Maybe look over here. L would be huge. So the difference in energy levels becomes, you can't even tell the difference anymore. What's M? Mass of the electron, or whatever's in the box, right? So mass of a baseball or whatever. Again, the energy differences between the two different energy levels, they become 0. Again, if you make it a really huge object. Okay. Boundary conditions. That's this whole part about X being between 0 and L. That's our boundary conditions. There's boundaries. Only certain wave functions are going to fit in there, if you want to think of it that way. Think of it as a standing wave. And only certain standing waves are going to fit in there. But so the boundary conditions are the reason why you have quantization in the first place. If we didn't have boundary conditions, there wouldn't be any quantization. So you got to have boundary conditions. Okay. And we have quantum numbers. They're just describing the state, right? You give the quantum numbers, you can describe that state, that wave function, and its corresponding energy. Okay. We mentioned 0 point energy. And correspondence principle. Here, that's another oddball one. And we talked about how you make the box really huge. You can't tell the difference between energy levels. When you make the mass of the object really big, you can't tell the difference between energy levels. Well, correspondence principle is when they're referring to really high energies. So they're not talking about the mass of the object. They're not talking about the size of the box. They're just saying, hey, you have really high energies, you can't tell the difference between energy levels anymore. So they call that the correspondence principle. I think this is kind of interesting how this turns out. Right? So we think of a particle in a box. So how do you tell one wave function from another, Gloriana? You just change what? For a particle in a box. Just change little.
The L?
Well, if you then you're changing the whole box. You need a whole different set of equations.
Oh, N?
Hey, change little n. That's your little quantum number. That's your counter. So if you change little n, you have a different wave function. Change little n, you're going to have a different energy. So you could have psi 1, psi 2, whatever, psi 3. You just write them out, right? And you can all write them all right there. And you could write what the wave function actually is. You're just changing n. What I think is really interesting is that they're all orthogonal. And what does that mean? That means if you take the integral, here it is right here. Take the integral of psi star psi and just make these n's be different. 1 and 3, 2 and 4, 8 and 10, whatever. They just need to be different. And every time that integral is going to be what? Now, what is an integral? Area under the curve. So they're trying to give you a hint here. They're trying to give you a hint, saying that, okay, look, this is what psi 3 looks like, and this is what psi 1 looks like. So they multiplied them together, and then they got this plot. Right, that's a psi 1 times psi 3. And you're supposed to hopefully see, maybe, what's the total area? 0. Every single time. You have just as much positive area as you do negative area. So they always equal 0. That's what orthogonal means. So you don't have to waste your time trying to figure out a lot of these integrals. They're orthogonal. Okay. In this case here. Okay. Here's the energy levels. They plotted them out. Here's their equation, right, to plot out those energies. And then they just plotted them out. And the energy separation gets bigger and bigger the higher n goes. They say classically allowed energies here. What does that mean? With these really high n's, all of a sudden classically allowed energies. Can you tie that in? They call that the what principle? They call that the correspondence principle. Classically allowed energies means what?
The energy that you can go up to this other distance.
Yeah, you can't tell the difference anymore. There's no quantization. You can throw baseballs whatever speed you want. That electron can take on whatever speed it wants. It's almost like it's escaped. There aren't any boundary conditions there anymore. It's kind of odd. And I think this is an oddball thing. And it's kind of, I think, showing some difficulties with quantum mechanics. But because it looks to me like the energy levels are, right? Aren't they more spaced out? All of a sudden, boom, they say, oh, high energy, correspondence principle, classically allowed. So I think that's an oddball thing, and it's going to take a little more investigating to talk about. But for now, we just leave it at this. What if we didn't have a particle in a box that looks like a line? Box is a bad word, right? It should be particle on a line is what it should be called. Because that's what it is. It's particle in a line. Here's a box. A box has two dimensions, right? It has this dimension and that dimension. There's a box. Okay? And it's not even really a box. It's a square. It should be called particle in a square. Because a box has three dimensions, right? So you had a bad choice of words. Probably because scientists aren't very good artists, right? You can't really draw. So we had particle in a line. We've got particle in a square. So then you get two dimensions, and the equation ends up looking like this. And the reason why they're bringing it up is not much really changed. You have L1 and L2 describe the square, or rectangle if they're different lengths. But what's interesting, I think, is if you go through the math and calculate the joules here, you'll get so many joules. And let's say if N1 is 1, just pick two numbers that are different. Doesn't really matter. And 2 is 2. You'll get so many joules, right? What if I switched it around? I made N1 be 2 and N2 be 1. Would I get a different number of joules? No.
You have that equation on here, right?
Yeah, I added it. Since I have all this time to dink around over there, I just added it. So I got tired of writing it. I knew I wouldn't want to write it out, and if I did write it out, you're not going to read my writing anyway. So, but the point is are these two different states?
Yes.
They're two different states, but they have the same energy. What was the word for that? Degenerate. They're degenerate, right? So it seems like every single state is doubly degenerate, as long as those quantum numbers are different, right? All these states are doubly degenerate. In 3 dimensions, what are they going to be? Right? They're going to be triply degenerate. It depends on which numbers you pick, right? I mean, you could have N1 be 1, N2 be 1, and N3 be 2 or something. And then you just move that 2 around, you're going to have triply degenerate. Okay. So I don't know how important that is. I don't know if that's even in the homework, but tunneling. So here's our particle in a box, right? They drew the wave function, and they're saying that, whoa. Now this is wave function. This isn't psi star psi. So let's find the probability density. This plot makes more sense. Where is it going to be at, right? There's some amplitude outside the box, but it's not supposed to be there. It's energetically impossible. It can't get there, and that's what they call tunneling. And you can get impossible. It can pass through these energetically impossible barriers, and when it does, it's called tunneling. And how do you get it to happen a little more often? Make the particle light. That would help. That can tunnel easier. Then also make this barrier not as thick. That would help too. Okay, but they're just saying, hey, that happens. Maybe you've heard of STM, scanning, tunneling, microscopy. Maybe you've seen like those black and white images of like the eye of a fly and that kind of thing. I should Google them and put them up there. But yeah, that's all done through STM imaging. Okay. So let's see if we can get started on these. We already kind of got started on number 4, right? We told you how to start number 4, right here. How would you start number 1? Yeah. All right. And for your psi, you're going to put in what, Mel? That's the terminology we were using, right? We would call this guy phi. That's right. So your psi then, yeah, your n times your phi. Yeah. So that's the starting point for that one. Jeffrey, how would you start out number 2?
Those brackets.
The bra and the ket, yeah, bracket.
And with p hat.
With p hat in there, that works.
And then the integral of psi star p hat psi eta.
Yep. And what p hat is, you just look it up. It's just h bar over I d dx. Okay, we have to put in our normalized wave functions. Limits go from 0 to L. Glorianne, how would you start number 3?
The first equation on this page. Oh, wait a minute. Wait, let me see.
Oh, we would get that as an answer if we had this as our wave function. That's the last question. That's question number 4. They want you to find the average energy for a particle described by that normalized wave function that we're going to get. Really similar to number 4, right? Because they're asking for average energy down there, too. What did we do there?
Omega.
And then omega is going to be what operator? P hat was momentum. Which one was energy? Anyone help her?
H hat.
H hat. What is it called?
Hamiltonian.
Hamiltonian. So our start there is H hat. Okay? So there's your homework, because the next class is this. We'll work on homework. Okay, so you might want to jot this stuff down since we got time.
Wait, what?
So the homework that's on here isn't due the next time we come?
Yeah,
in?
we're
It's
gonna
the handout?
we're going to work on this homework next class period. All that you're going to work on the rest of the hour today is this, and then that's also your homework, what you don't get done. Right? So we'll spend the rest of the hour working on this, and then when you come on Monday, we're going to work on this stuff in class.
Oh,
Okay?
that's weird.
So it's a little bit of a change.
So then our day 4 is where we start the vibrational motion?
Day 4 would be this, yes. That would be day 4.
It's a different
Yes.
order.
Yeah, I changed it. So make sure you get all these questions written down.
Can you just email it to us?
Can you print it
Can you
out?
take a picture?
Oh, yeah. Because class is over anyway. Or you can take a picture. I'll go email it.
It's over already?
Oh, no, it's 1:50.
Yeah, it's over already. My bad.
Yeah, shit. I always get so confused here. We start at 1:15, so we go to 2:05. Right, Gloriana?
Yeah.
Jeez. This is so confusing.
Are you gonna print it out for us? Come on.
Yes.
Your fault, he's sending the wrong
Yep.
one.
It is my fault. I sent in the wrong one.
It is.
All right. So I'm going to,
X squared.
I'll go print them out. That'd be easier. That'd be better than having you print it out yourself. Actually, I don't even have to because it's online.